Okay, so today we are going to do an overview of. Last week we talked about the laws of illumination. For the past 2 weeks we have been talking about illumination. Ibrahim, mute your mic. Good. So illumination, as I had talked, as I had said, it's all about lighting. It's all about illuminating a room. So there are several principles of illumination. Besides you learning this unit so that you can attempt your exams when the time comes, it's also important for you to know the application, how you're going to apply this in your course, how you're going to apply this in your profession. So it is a very important topic. So I'm going to go through the overview of certain things, certain basic things that we are supposed to learn. So to be an optical engineer, now that you guys are going to be electrical engineers, you're going to do design. And for you to do design, you need to know about light. If I want to illuminate a room, how am I supposed to do? And for an illuminating engineer or somebody who is working with light, you have to know if I want to put light in this room. What is the use of the room? How is it going to be located? What is the natural illumination? That is the light coming from the ultraviolet rays. We had already talked about that. And what is light? Light is simply a very small part in the electromagnetic spectrum. The sandwich between ultraviolet and infrared radiation. So the visible portion of the electromagnetic spectrum extends from about 380 up to 780 nanometers. So those are the speeds of light. So what distinguishes this part from the electromagnetic spectrum from the rest is that the radiation in its region is absorbed by the photoelectrons of the human visual system and hereby initiates the process of seeing. So it is the rays of light that comes from the spectrum that enables the visual part, somebody to see. So it's important to know. Yes. It's important to know about that. Then the visual spectrum, it's generally associate. Ibrahim. Uh, the visible spectrum, that is the ultraviolet radiation, sometimes incorrectly referred to as the UV light, has shorter wavelength and visible radiation light. So uh, the infrared radiation are also the basic concepts in optics. We have the reflection. Now, how are we able to see? We have the when you want to see the spectrum on a polished specular on a rough surface that is spread out, and then we can see now how light is emitted. We can see the reflected light and the source and the reflected light. So it is this reflection on a surface that enables people to see. So the specular spread and diffuse reflection from a surface. Specular reflection demonstrates the law of reflection, which states that the angle between the incident ray and the line that is normal, that is perpendicular to the surface, is equal to the angle between the reflection ray and the normal ray. So that is now the angle of reflection and the normal angle. And then we have the angle between the incident ray and the normal is called the incident angle. Reflection, that is the Snell's law. With light travels when light travels from one material to another, some some from air to gas, it refracts, bends, and changes velocity. So the refraction depends on two factors, that is the incident angle and the reflected angle. These ones are the basics of light. The index of the refraction of a particular material is the ratio of the speed of the light in a vacuum and the speed of light in the material. So the speed of light in air is almost identical to the speed of light in the vacuum. So the index of refraction for air is considered to be that. And then the index of refraction is for almost all other substances is greater than 1. That is because the speed of light is lower and it passes through them. Now, where you can see now there, N is the refractive index of the medium 1, N2 is the refractive index of the medium 2. Those who guys who took physics, you were able to see this when you are in high school. That is N sine theta is equals to N2 sine theta. That is the Snell's law. So those are the index of refraction, and the materials are there. We have diamond, that. Those are some of the basics in the refraction of light. Now, refraction example. Reflection, an index of refraction. A transparent, now that is an example of a question. Now you can see 100% air is here, and this is 10% refracted beam. When light hits a material, that is, and the light is reflected, and another one is refracted. So the transmitted beam of light is there, and then the reflected light. Now this reflected light is what gets the human eye, and the person is able to see. The person is able to see what is happening in a certain room. We have an example there of the refraction. The transparent substance transmits almost all light, but it reflects the light, a bit of light from each of its two surfaces. So this reflection occurs whenever light travels through a change in the refractive index. So at normal incidence, that is the Fresnel's law of reflection, quantifies the effect. The total internal reflection and dispersion is also there. I want us to go up to now the transmission of light. You can see how the transmission of light and now the Lambert's law comes in. So the transmission of light. When light passes through an object, it is called transmission. Absorption, refraction, and diffusion all affect light transmission. So absorption, what is absorption? Absorption, instead of completely transmitting light, an object that can absorb part of all the incident part or all of the incident light, usually by converting it into heat. Many materials absorb some wavelengths while transmitting others, which is called the selective absorption. So it absorbs some light and another one is not absorbed. So the Lambert's law, you can remember we talked about the law, the Lambert's law. The Lambert's law of absorption states that the equal thickness of a given homogeneous material absorbs the same fraction of light. Now, if in another words, if a 1 centimeter block of material absorbs a half of the incoming light, then the second 1 centimeter of the same material would absorb a half of the same of the beam. Now it goes by half. It is direct. We say it is inversely proportional. Inversely means it goes as it reduces. Therefore, so that only 0.5 times 0.5 or 0.25 so of the original light is transmitted through a total of 2 centimeters of the material. I hope that one is clear. And then the exponential relationship is given in the formula. And then we said that the intensity is transmitted of light, that is I, is inversely proportional to the surface. So intensity I is the intensity of light entering the material, excluding the surface reflection. And then alpha is the absorption coefficient in the inverse length units. X is the thickness of the sample measured in the same as thickness. And then note the complete accuracy. Each wavelength must be considered separately. So the Beer's law further breaks down the absorption coefficient and into two variables. So beta and absorption per unit concentration coefficient, and C, the concentration of the material. Now the law states that equal amount of absorbing, you can now see equal amount of absorbing material such as the dye of a liquid absorb equal fraction of light. For example, The figure shows that the twice as much as the dye in the same volume of material absorbs twice as much light. So as which Lambert's law of absorption, each wavelength should be considered separately by the Beer's law. Now you can see what is happening here. So if we have a light source here, then this one gets a whole 1 unit, this will get a half, this one will get a half of the half. So it goes as it reduces up to the end part or the last part. What about diffusion? Diffusion, when light strikes a perfectly smooth surface, the reflection is specular, as explained in that section, that is reflection. So the light strikes the rough surface, the light is reflected or transmitted in many different directions at once, which is called diffusion or scattering. So diffusion is there, it can move on the other side, on the below side, or on the other side. That is, if you can see if this one has a shade. Now, like for example, a mirror, which is a transparent part but then has some shading at the back, so the diffusion happens backward. But if it is something like it's colorless, like the window panes that we have, then the diffusion takes in inside. So the diffusion and reflection, the amount of diffuse transmission of reflection that occurs when light moves through one material to strike another material depends on two factors: the difference in refractive index between the two materials, the size and the shape of the particles in the diffusing material compared to that of the wavelength. Now, for example, the molecules in an air happen to be the right size to scatter light with shorter wavelengths, giving us a blue sky. Now, one method of describing diffusion is the bidirectional scatter distribution, that is BSDF, which quantifies the scatter of the effect. But you can see it from the picture here correctly how it looks like. And then we go to another one is flittering. What is flittering? The transmissive flitter is a material that absorbs some wavelengths and transmits others. So while a refractive filter absorbs some wavelength and reflects others, for example, a red filter absorbs all but the longest wavelength of visible light. A reflective red filter reflects a longer wavelength, and the transmissive red filter transmits the longest wavelength. So you can hear now about the filter. The basic the principles are there: the wavelength, uh, those ones. Then the spectral response. Now, even when the narrow spectral visible light and human eye is more sensitive to some wavelength than others, this sensitivity depends on whether the eye is adaptive to the bright light or darkness, because of the human eye contains two types of photoreceptors, that is the cones and the rods. So when the eye is adaptive for the bright light, called the let me zoom so that the photopic vision. Now the luminous level generally greater than 3.0 CD, that is the candle per meter squared, and the cones dominate. So between that, this is now, it helps us to understand the response of the eye towards the amount of light that comes. Now when you look at this, the luminous efficiency function. So when this is the wavelength, this is the relative value, how it varies, and the photopic scotopic is there. And then the solid angle. The solid angle is the three-dimensional equivalent of a two-dimensional angle. And then now that is still under radiation, the radiant and the luminous energy. You can see now the radiant luminous flux is there. The luminous flux, we had already defined about it. Denotes that is measured in lumens. It is measured in lumens, and the CIA defines the lumen as terms of luminous flux of monochromatic radiation. So this is a Stadian solid angle removed from a sphere. You can now see the part of it that has been removed from that sphere. Spectral luminous efficiency, you can see that. I want to go direct to now we can have the radiance. You can see the radiance and luminance. We had talked about the how how the light moves using the solid angle, that is 1 radian has a projected area of 1 square feet of the distance of this. We had discussed this in the last time. Then the radiant and luminous intensity. Now the radiant intensity, denoted by the letter I, is the amount of power radiated per unit solid angle, that is measured in watts per stadian angle. And then we have the luminous intensity I is the fundamental SI quantity of the photometry. The candle is the fundamental unit from which all other photometric units are derived. So the basic radiometric and photometric measurements, that is the inverse square law. I'm going through all this so that you can have the basics. You remember last week we talked about the inverse square law, and we said that as a surface that is illustrated in the light source moves away from the light source, so the surface appears dimmer. So in fact, it becomes dimmer much faster than it moves away from the source. So the inverse square law, which identifies this effect, relates to illuminance, that is E, and the intensity, that is I. And we said that the illuminance is equals to intensity over the square over the area, or the square of the distance. The inverse square law is there. You can see we had talked about it. And the Lambert square law is also here. We had also talked about it, so I'm not going to focus on it much. The Lambertian emission and reflection. So we need to know this because it's going to help us in the calculations when we'll be talking about the calculations of figures. So the Lambertian surface reflectors or emits equal isotropic flux in every direction. For example, in evenly illuminated diffuse flat surface, such as a piece of paper, is approximately Lambertian because the reflected light is the same in every direction from which you can see the surface of the paper. Now, however, it does not have isotropic intensity because of the intensity varies according to the cosine law. Now, the figure you can see the figure 4.4 shows the Lambertian reflection from the surface. Notice that the reflection follows the cosine law. The amount of reflected energy is in a particular direction, that is the intensity, is proportional to the cosine of the reflected angle. So remember that the luminance is intensity per unit area. So because both intensity and the apparent area follow the cosine law, they remain in proportion in each of the other viewing angle changes. Therefore, luminance remains constant while luminous intensity does not. So you can see at this angle, maybe this is the source of light. And now in the reflection, at this angle, the reflection is 100 depending on the angle. At this angle, it's 30, 60, and then 80, and then 50 respectively. So we go to the light sources. The light sources. The lighting industry makes millions of electric light sources called lamps. Those used for providing illumination can be divided into three general classes, that is, incandescent lights, discharge lamps, and the solid-state lamps. The incandescent lamps produce light by heating the filament until it glows, and then the discharge lamps produces light by ionizing gas. Those are the discharge lamps. They ionize gas through electric discharge inside the lamp. So we are going to keenly look at these different sources of light. Now, the solid-state lamps are of a phenomenon called electroluminescence. to convert electrical energy directly to light. So, in addition to manufactured light sources, daytime sunlight received on the Earth, either directly or from the sun, scattered and reflected by the atmosphere or reflected by the moon, provides illumination. So, the prime characteristics of daylight is variability. Daylight varies in magnitude, spectral content, and the distribution of different meteorological conditions at different times of the day and of the year. So when we look at that, now illuminance of the Earth's surface produces a daylight can cover a large range from 150,000 lux to on a sunny summer's day to I have my scale to 1,000 lux of the heavy overcast day of winter. So incandescent lamps, we can see the incandescent lamps here. The incandescent lamp technology uses electric current to heat coiled tungsten filament to incandescence. So the glass envelope contains a mixture of nitrogen. Now you can see these are the normal bulbs that we have, the normal lamps, the Philips that we use. They're called what? They're called the normal bulb holder bulbs. Now, what are they? The glass envelope contains a mixture of nitrogen and a small amount of the inert gases. It contains a mixture of nitrogen and small amount of inert gases such as argon. So, some incandescent lamps, such as some filament lamps, also contain xenon. Now, some of these incandescent lamps are called xenon lamps, but are not the same as high pressure xenon lamps discussed in the next section. So, incandescent lamps have come long way since the Thomas Edison's first carbon filament lamp, which, when introduced in 1879, had a life of about 40 hours. So today, commonly available incandescent lamps have average lives between 750 to 2,000 hours. So the figure this now shows the construction of the typical incandescent lamps, while some commonly used bulb shapes are shown in the figure. So you can see the construction of a typical incandescent lamp. Now we have the tubular of them, the candle-like, the flame shape, the A-type lamp, the global G lamp. Now, the incandescent lamps are strongly affected by input voltage. For example, reducing the input voltage from the normal 110 volts to 104 can double the life of the standard of the incandescent lamp, while increasing the voltage to this normally can halve the life. So voltage variation, so you realize that when the voltage is very high, the life is lower, and when the voltage is reduced, the life gets longer. So the voltage variations also affect light output, lumen, power watt, and the efficiency. That is the lumen per watt. You remember we talked about the efficiency. So this is how the performance of the normal lamps, the ohms, the amperes, the lumen watts, and the lumens. And then we go to the halogen lamps. Unlike the incandescent lamps, halogen lamps use a halogen gas fill that is typically iodine and bromine to produce what is called the halogen cycle inside the lamp. So we have halogen cycle, halogen gas contained with the tungsten, you can see now there. And then we go there, and then tungsten halogen lamp has several differences from the incandescent lamps, meaning the lamps have longer life. The bulb's wall remains cleaner because the evaporated tungsten is constantly redeposited on the filament by the halogen cycle. Now, this allows the lamp to maintain the lumen output throughout the life. The higher operating temperature of the filament improves luminous efficiency. That is, the lamp produces a whiter or cooler long, which has a lighter correlated or color temperature. Those are now the incandescent lamps. Now, the bulbs are more compact, offering opportunities for better optical control. Now, halogen lamps are sometimes called the quartz lamps because their a higher temperature requires quartz envelopes instead of the softer glass used for the incandescent lamps. So we have other types of lamps called the discharge lamps. Discharge lamps produce light by passing an electric current through a gas that emits light when ionized by current. So an auxiliary device known as a ballast supplies voltage to the lamp electrodes, which have been coated with a mixture of the alkaline earth oxides to enhance electrode emission. So two general categories of the discharge lamps used to provide illumination are the high intensity discharge and the fluorescent lamps. So the high intensity discharge, we are going to now to look at them. What are they? The high intensity discharge lamps, 34 types of the high intensity discharge lamps are the most widely available in the today's market. So the high pressure mercury vapor lamps, metal halide lamps, high pressure sodium lamps, and xenon lamps. So now you can look at how they look like, and these are very important parts to be covered in your topic because this one normally does not miss in your examination. So the high pressure mercury vapor lamps. So the high pressure mercury vapor lamp light is produced by an electric discharge through a gaseous mercury. So we normally have a gaseous mercury that is normally there. So the mercury typically along the argon gas is contained within the quartz air tube, which is surrounded by an outer bulb of the may also be used in high-pressure mercury vapor lamp to aid the searing time and does not significantly change the visible spectrum of the lamp. You can now see it. We have the quartz tube, we have the argon-filled gas, the starting electrons are here, the main electrode is there, the starting resistor, the neon-filled gas, the main electrode, and the outer bulb. So that is how it looks like. What about the metal halide lamps? The metal halide lamps is a mercury vapor lamp with other metal compounds known as halides added to the arc tube to improve both color and luminous efficacy. So shows the construction of a typical single-ended screw-based metal halide lamp. Another one is the high pressure sodium lamp. Now you can see, you need to see the differences between these two when sometimes you will be asked to do the construction and the working of this type of lamps. You have to know how to draw them and the differences between the two, the four of them. That is the light produced in the high pressure sodium lamp of the electric discharge through combined vapors of the mercury and sodium with the sodium radiation dominating the spectral emission. So the hard gas outer bulb may be clear or in its inner surface may be coated. The diffuse power to reduce the brightness of the arc tube. So you can see it, how it looks like. Again, we have a vacuum there, the gas bulb, and then the xenon. Sorry, somebody has written something here. Oh, slide gani, is it this one? Salad, can you unmute and tell me? Yes, which one is hii ama gani?
hiyo tumepita sai.
Yeah, metal halide.
Yeah, this one.
Oh, so you see how it looks like? So the metal halide lamp is a mercury vapor lamp with other metal compounds known as the halides. It has some halides in it. And then added to the arc tube to improve both the color and the luminous efficacy. So showing is the construction of the typical single-ended screw metal halide lamp. So you can see this is just a construction. So sometimes you will be told in the examination to draw the construction and maybe the working of these lamps. So the working is the same. We said the high intensity lamps, they work the same. So all of them work the same. It's only that the construction vary. So is that okay, Salad?
Yes.
Okay, we move on. Then now we have already talked about the high pressure sodium lamps. These are the light is produced in a high pressure sodium lamp by an electric discharge through combined vapors of mercury and sodium, with the sodium radiation dominating the spectral emission. So the hard glass outer bulb may be clear, or its inner surface may be coated with a diffuse powder to reduce the brightness of the arc tube. So that one I think is it's clear. And then we go on to the xenon lamps. You can see how they look like, the xenon lamps. Unlike other three, the high intensity discharge lamps described here, xenon lamps do not contain mercury vapor. They contain xenon gas. You can now see, kept at a pressure of several atmospheres. So xenon lamps are available in watts from 5 to 3,000 watts. Shows some examples of xenon lamps. So some incandescent lamps, such as some flashing lamps, also contain xenon. So these incandescent lamps are sometimes called xenon lamps, but are not the same as the high pressure xenon lamps. So you can see them. We have the fluorescent lamps. So up to there, we are done with the high intensity discharge lamps and how they look like and what they contain. Yes, before now we proceed, I would like to get any question before we go to the fluorescent lamps. A question?
No.
You are okay? So we go to
Yes.
fluorescent lamps. Fluorescent lamps. The fluorescent lighting accounts for 2/3 of all the electric lighting in the United States and in the world. Fluorescent lamps are everywhere. So the fluorescent lamp is a gas discharge source that contains mercury vapor at the low pressure, with a small amount of inert gas for starting. So once the arc is established, the mercury vapor emits ultraviolet rays. So I repeat again, fluorescent lamp lighting accounts for 2/3 of the electric lighting everywhere. Now the fluorescent lamp is a gas discharge source that contains mercury vapor at low pressure. That is very important for you. It contains mercury vapor at low pressure with a small amount of inert gas for starting. It has only a small amount of inert gas for starting. That is just for starting purposes. Then once an arc is established, the mercury vapor emits ultraviolet radiation. Now, fluorescent powder, that is phosphors, coating in the inner wall of the glass tube respond to the ultraviolet radiation by emitting wavelengths in the visible region of the spectrum. So ballasts, which are required by both fluorescent and the HID lamps, provide a necessary circuit conditions, that is the voltage, the current, and the waveform, to start and operate the lamps. So we have two general types of the ballast are available in the fluorescent lamps, that is the magnetic electronic. That is electronic ballast, often most expensive, but are usually lighter, quieter, and emits the lamp flicker associated with magnetic ballast. So the fluorescent lamps are often described in terms of the diameter of the lamp tube. For the designation of the diameter is given in the 8 inches. Now, for example, we have the T8, that means 8 inches, the lamp. So the linear fluorescent lamps. Now, how it is, the parts of it. The linear fluorescent lamp range in length from 6 inches to 8 feet, that is 8 inches, and in diameter of 2 per 8 inch, that is T2. T2 is T2 is it means that it is 2 per 8 inch, and then 2 per 1 2 to 1 of 8-inch, that is 2T17. We have very long fluorescence. Their power ranges from 14 to 215 watts. So this figure shows the construction of a linear fluorescent lamp. Let me zoom out so that you can see the diagram. The outer bulb is there, the electrode is there, the mercury filled gas is there, and the phosphorus or linear wall of the tube. And the pin is also there. Construction of the linear filament. You can see that.
Teacher,
Mm-hmm.
kwa hiyo
Yes.
diagram blast iko wapi?
Eh?
Blast.
Acha niangalie. Ati kwa hiyo diagram blast iko wapi? The magnetic blast ziko na flicker associated with magnetic blast. Unaona? Not all of them utaona hiyo. Unaona ziko na different making. The fluorescent tubes. Unajua tubes zinakwanga zingine hata ziko coiled, zingine ziko, but most of it iko hapo kwa electrode. Hapo kwa electrode, it is connected to the where the mercury filler gas is there. Are you seeing that? So that connection, that extension from that part to the electrode is there, is what is called the magnetic blast. So
Okay.
then we go to the compact fluorescent lamps. And you know, I told you that the fluorescent lamps is zile tu za T ama nini. There's many others. So we also have different types of fluorescent lamps. We have others called the CFLs, or the compact fluorescent lamps. The allow it to try and reconnect again. Okay, that one is now okay. You can see we have from T, that is the 5-inch, to 8-inch, that is the T5 or smaller, and the CLF power ranges from 5 to 55 watts. And the figure is not there, but you guys can look at the figure, can get the figure from, you can Google and see how the CFLs look like. So those are the fluorescent lamps. So we now go to the LEDs, or the light emitting. LEDs are solid-state semiconductor devices and converts electrical energy directly into light. So LEDs can be extremely small and durable. Some LEDs can provide much longer lamp life than other sources. So the figure this shows a different LEDs from several typical LEDs. The plastic encompasses and the lead frame occupy most of the volume. So the light generating chip is quite small, typically a cuboid with one side equal to 0.25 the clip, a solid crystal material. When current flows across the junctions, different materials. So the composition of the materials determine the wavelength of their color and or light. So you can see the chip, the LED, the sub-miniature LED, the lamp overall, the high flash emitter, and the very high emitters. So you normally see the LEDs when they are installed. The LEDs range from those ones that we even use in projects to those that are downlighters and any other thing. So the common luminaires are here. The contact and then the approximate luminance, you can see them. The common lamps luminaires, the different sources generate wide range of luminance. You can see them, and that is a table. Common lamp efficacies are there. The spectrum and color, I'm not going to deal so much on that. I'm not going to deal so much on that because of your syllabus. So up to that point, before we go to the other slide, I want us to go to the discussion. I've already posted a discussion. The discussion is going to take exactly 50 minutes. It's 40 to 50 minutes. So we are going to discuss. I want people to post their ideas there. So after that, we'll come. That is at exactly now 50 minutes from now. That is 12:55. We'll be back at the big blue button to discuss about the other slide so that we finish the lesson. So I want to hear any question before we can break for the discussion. Any concern? Yes, Salad.
Niko sawa madam.
What about Ibra?
Anaingia kipotea.
So wakati ataingia mwambie tuko kwa discussion sahi. So go to the discussion and see what I posted there, and I want the conversation there so that I've already posted some questions. Ibra, we are now going to the discussion part. So we are going to come back here at exactly 12:50 or exactly 1. Let me say exactly 1 so that we can go to the other slide. So you guys log to the portal and click on the discussion. I've already named it there. It is week 4 discussion on illumination. So let us go there. So I'm waiting for you on the discussion side.
You are currently the only person in this conference.
Asante. Asante.
You are currently the only person in this conference. You are currently the only person in this conference.
Ile ko. Aku Haro?
You are currently the only person in this conference. You are currently the only person in this conference.
Hello? Mic testing.
You are currently the only person in this conference.
Hassan. Sarad. Madam.
Sema Ibra.
Sasa labda akuje tumwambia tumejaribu ikakataa.
Akikuja. Bado hajakuja.
Yaani leo watu wamekataa kabisa kukuja.
Watu wamekataa kuja. Umefanya nini kati ya ngao?
Ya jana. Ya electrical principles 2. Nilifanya.
Ulifanya yote? Ukapata ngapi?
Bado sijaangalia lakini kuna zenye alikuwa hebu niangalie nitakwambia.
Poa.
You are currently the only person in this conference.
Yes, madam.
Hassan, I didn't see you guys doing any discussion.
Si nimekutumia sioni kitu.
Kwa nini amuoni na nimepost hapo? Ilikuwa inasema ati you are not in any group.
Niambia hivyo.
I think ni kitu nilikuwa nime deactivate hiyo kitu.
You are currently the only person in this conference.
Hello.
I've already deactivated that group thing. Hata hiyo time umenitext kwa WhatsApp nilikuwa na issues with logging in. So imekubali I've deactivated but now you will have to discuss after tumemaliza.
Sawa.
Let us do. Na Ibra amepotea.
Atarudi labda.